Alright guys, welcome to our channel Code with Sunny, and today we will be discussing the medium problem of the LeetCode subarray sum equals k. Its index is 560. Okay, so the basic prerequisites required to solve this problem is like you need to have a good command over hash table. Like you need to know how we can use hash table to count the total number of continuous subarrays whose sum equals k. That is this problem. Okay, so yes, also if you are not aware about the hash table, how we are going to use that in this problem, then you can come over this similar question section. At least you can do the problems called two sum, and like yes, you can also do this problem like continuous subarray sum. Then in that case, like if you are able to do that, then you have a good idea how we can use that same concept to solve this problem efficiently. Okay, so let's begin. Given an array of integers nums and an integer k, return the total number of continuous subarrays whose sum equals k. We need to consider every subarrays. Like subarray is actually the continuous segment of the current array. Okay, yes, yeah, and we need to find that sum, and if that sum is equal to k, we need to return, we need to return all those subarrays whose sum equals k. Okay, so you can see the max length of subarray goes around 2 into 10 raised to the power 4. So O of n square times solution is not going to pass. So we need to consider an efficient method to solve this problem, right? So we would be using a hash table. I will tell you how we can improve our code by using that. For now, let's understand how we can solve this problem with the same concept. Okay, so what I'm going to do is like we are going to pick a small example, and yeah, then we will consider how we can improve that. Consider an array where every element is has the value 1, and let's choose the value k right now. Let's say we have k as 2, right? We need to find all those subarrays whose sum is exactly equal to k. So the very first approach is what we are going to, like the very first idea that is going to strike to your mind is like consider a brute force solution. Brute force. What is this brute force solution? It is nothing but a O of n square times solution where you will consider every subarray, right? Let's say subarray this one, like yeah, this subarray, or this subarray, this one, and you have this one, or this one, or the entire length subarray. So finding out that every, like fixing the two bounds of every subarray will take O of n square time, and finding out the sum can be pre-calculated, and it will take O of 1 time to find out that sum, and the comparison will again take O of 1 time, and you can do that, like increment your count when the sum is exactly equal to k. Okay, in this case you can see this is this is one of the subarrays whose sum is exactly equal to k, and another subarray is going to be this one. Okay, so yes, how like O of n square time solution will not pass, will give you a TLE verdict. So we would be considering an efficient solution. How we are going to do that? Can you think upon that, how the prefix sum, if we are able to find out the prefix sum of this array, will help us to find all those continuous subarrays whose sum is exactly equal to k. So for an instance, let's try to find out the prefix sum of this array. So it will come out to be 1, then it will come out to be 2, and it will come out to be 3. Okay, so just tell me one thing, that if you have been asked that what is the subarray sum, let's say we are talking about this subarray, right? Let's say we are talking about this subarray. So we need to find out the sum of this subarray, like subarray containing only a one element. So what we are going to do, we will always subtract the prefix sum up to this point, which is nothing but 2, minus prefix sum up to this point. Okay, this is what we are going to do, which is 1, which will come out to be 1. You can see the value is same over 1 over here. So let me write down a general equation that may help you to understand the concept, which let's say sum up to 0 to r minus sum up to 0 to L minus 1. Let's say this is actually L. Okay, so you can see where L is going to be less than or equal to what, R. Now this term can be written as, let's say we have a prefix sum array, we will do like that, pre-sum of R minus pre-sum of L minus 1. Okay, so this term will always give you the sum of the subarray in the range L to R, if I am not wrong. You can just verify it. You can see prefix sum up to R. If you will subtract the prefix sum of up to L minus 1 from this value, prefix sum of up to R, then we will get the subarray sum from L to R. And if you notice the problem, we have been asked that what are the total number of subarrays which will satisfy this condition, like is exactly equal to k, right? So how we can track the like frequencies of total number of such subarrays with the help of this equation. Okay, so if you are able to understand that, if we can rearrange this term, you will get like a prefix sum up to r is exactly equal to yes, no, I'm not going to do like that. It will make you understand in much more complex way, so I will write down this type, like prefix sum up to, like I will just rearranging the terms. Let me write down the first prefix sum up to r minus k, that is I have removed this term to the right and bring k to the left, and it will be something like this one. So you will have prefix sum up to L minus 1 must be exactly equal to prefix sum up to R minus K. Okay, so if you have been asked to find all those subarrays which will satisfy this condition, so you are going to ask yourself the one statement. Let me just tell you what is that statement. If you have been asked that what is the total number of subarrays, total number of subarrays ending, total number of subarrays ending at index R, and sum of that subarray is exactly matching with K. Okay, if you are not getting it, no need to worry about. Let us understand with the help of example. Let's say our R is at this position. I am just asking you that what is the total number of subarrays whose right bound of that subarray is always at this position, like always at this position, and left bound can be among any index which is L less than equal to R. I'm talking about this thing. So it can be only one length subarray, or it can be two length subarray, or it can be the entire length subarray. Okay, so I'm talking about total number of subarrays ending at index R, and the sum is exactly equal to K. Okay, now coming back to this equation. Okay, so you can see if sum is exactly equal to K, and if we will follow this equation, which is prefix sum up to R, we will have that value minus K must be exactly equal to prefix sum of L minus 1. Then we can say that that subarray is going to be having the sum is actually equal to K. So what I am going to do is I am going to keep track of prefix sum for all I less than equal to R. Like if you are calculating for the rth index, then I will keep track of all prefix sum for all I less than equal to R in a hash table. Like I will count down the frequencies. Like let's say we have the prefix sum have value 1, 2, 3, right? So I will say that frequency of 1 is 1, frequency of 2 is also 1, frequency of 3 is also 1. Suppose we have another I whose value is like whose prefix sum of I is let's say again 1, then you will increment its count to 2. Okay, note that I should be less than or equal to R for if you are calculating for the current index. Okay, so if if we want to find a total number of subarrays, then we will find this value prefix sum of r minus k, and we will find out those l minus 1, those index l whose value is exactly equal to this value prefix sum of r minus k. Okay, and suppose let's say we are saying that we are going to find for k equal to 2. So what I'm going to do is, we are at this index r, you can see I will find out 3 minus 2, which is exactly equal to 1, right? So our hash table will contain the frequencies like this one. 1, note that this is actually I less, strictly less than r. Okay, so this will not, this won't become. So what I am going to do is, I will search for the total number of frequencies whose prefix sum value is exactly equal to 1. You can see the frequency of 1 is 1, frequency of 2 is also 1. So you can see there is exactly one frequency of 1. So it means that we have a subarray starting from this one to this one whose sum is exactly equal to 2. Suppose there exists another one whose prefix sum value is also, there exists another index I whose value is also 1, so this will become 2. So there exist two subarrays, and that subarray is ending at index r and having that sum exactly equal to k, because we are following this equation, prefix sum of r minus k must be matching with prefix sum of l minus 1. Okay, so we will keep track of all the prefix sum of I, and for the for calculating at the current index, total number of subarrays ending at this current index, then we will find out the value prefix sum of r minus k, and we will find all those frequencies which is matching with this value. And if we got that value, then we will increment our answer by that value, which will be the total number of subarrays ending at the current index r. In that case, we will do that for every index, then we will get the total number of subarrays in our original array, which has the sum exactly equal to k, right? So let's begin the coding part, how we can implement that efficiently. Okay, so yes, so let me show out you the logarithmic time code like n log n. Then we will use a unordered map to implement that in O of n time for an average case. Okay, so for now you are seeing the time complexity of this code is like O of n log n, and the space complexity is O of n, right? Because we are using a map, and n log n because we are iterating the array n times, and insertion will take logarithmic time. Okay, so I have a table map int comma int table. I will increment the value 0 by 1, because we can have a prefix sum. We can have if you're calculating for the current index, the the required subarray can be the can be the prefix of the original array. That is why we are going to increment it by 1. So prefix sum of 0 will be starting with 0 and answer will 0. So first I will increment the sum up to the current index, then I will try to find total number of frequencies of the prefix sum which is matching with this value. If we are able to get that the value, we are going to increment our answer by that value. Also, after doing that, we need to keep track of prefix sums for every index, we need to insert that into our table. So we will be doing over here. Okay, so this will take n log n time and O of n space. And let me talk about O of n time solution also. The idea is totally similar, but yes. Okay, so yes, you can replace this with this is not O of n log n, this is actually O of n, because average time of insertion in the unordered map is actually O of 1. So it would take O of n time as an average. Okay, so you need to forget this one. This is actually O of n, and the space complexity is O of n also. So you can see the idea is very much similar, totally similar, just we have replaced map with unordered map. Okay, so if you guys have still any doubts, do reach out to us in the comment section of the video, and thank you for watching this video.